You ever notice how one headline can make it sound like the sky is falling, but the actual numbers are just sitting there, quietly disagreeing? Because 3i Atlas just drifted again. People online are yelling, "It changed course," like it hit a steering wheel. But when you line up the tracking data, the math tells a calmer, weirder story. Subscribe, because in the next few minutes, we're going to separate what the cameras show from what the orbit proves. And that gap is where the real mystery lives. Here's what's happening in plain English. 3i Atlas is an interstellar visitor. That means it didn't start here. It's passing through, and we're trying to measure its path using tiny, tiny changes in where it appears against the stars. Not vibes, not it looks like it moved. I mean real astrometry. Timestamps, sky positions, error bars, and a lot of people checking each other. This is the same kind of work that teams feed into the Minor Planet Center, and the same kind of orbit modeling NASA's Jet Propulsion Laboratory is famous for with their Horizon system. And it's the kind of thing that decides whether an object is simply drifting or truly accelerating in a way gravity alone can't explain. Now, why are the numbers not matching the headline? Because headlines usually talk like this. It changed course, it turned, it aimed, but orbits don't work like a car. In space, course change can mean a bunch of boring things that look dramatic if you squint. It can mean we got new measurements that tighten the orbit solution. It can mean a measurement was off and later data corrected it. It can mean the object is outgassing like a comet, creating a tiny push. Or it can mean the model we used didn't include a small force and the residuals start piling up. Residuals sounds like a dusty word, but it's basically this. You predict where the object should be, you look where it actually is, and you measure the difference. If the differences are random, you relax. If the differences line up in a pattern, you pay attention. And here's our first little climax of this report. When people say 3i Atlas drifted again, what they really mean is this. The predicted position and the observed position are not hugging each other the way you want. There's a gap. And if that gap grows in the same direction over time, you don't get to shrug it off as telescope noise. But here's the trap. The internet wants one of two endings. Ending A, aliens. Ending B, nothing. Real science usually gives you ending. It's probably natural, but not normal. And it forces you to learn new details you didn't care about yesterday. So we're going to walk this like an actual NASA-style investigation, the way you'd hear it from people who work with messy data for a living. Step 1, check the obvious fakes. Spacecraft quirks, processing artifacts, and nature making geometry, because nature loves geometry. And humans love to mistake geometry for intention. Let's start with the simplest thing that breaks hearts. Sometimes the drift isn't in the object, it's in us. Different telescopes have different pixel scales, different distortions, different ways they see stars near the edge of a field. Even the atmosphere can warp star position slightly. If you're combining observations from multiple sites, small systematic errors can stack. That's why professional observatories obsess over calibration. That's why a place like the European Southern Observatory can produce clean measurements night after night. That's why Keck in Hawaii is such a big deal when it comes to faint targets. And that's also why we're excited about the Vera Rubin Observatory coming online for wide field discovery and tracking. It's not just about pretty pictures. It's about dependable numbers. And here's the second climax, because it's sneaky. A lot of course changes on social media are just orbit updates. Early on, you have fewer data points, bigger uncertainty. Later, you add more, and the best fit path shifts slightly. People screenshot the old path, compare it to the new one, and scream, "It turned." That's not a turn. That's a better estimate. So what makes this case different? Why are we even talking about it? Because 3i Atlas is not only hard to track, it's also an object type that loves to mess with models. If it behaves like a comet, it can create its own tiny thrust by releasing gas and dust. You don't need engines. You just need sunlight warming the surface, ice turning into gas, and that gas carrying momentum away like a tiny rocket. Comets do this all the time. It's natural. It's messy. and it can look like deliberate steering if you don't model it. This is where Hubble spectrograph records have historically mattered for comets, because spectroscopy can tell you what's coming off the surface: water, carbon dioxide, carbon monoxide, other molecules. With JWST, you can do a lot in infrared too, which is why people obsess over JWST frames. It's not just a photo, it's a clue about chemistry and heat. So we ask, is the drift consistent with non-gravitational forces? That phrase sounds like a villain's name, but it's just a category. Anything besides gravity. Outgassing is the big one for comet-like objects. Another is the Yarkovsky effect, which is more common for asteroids over long time spans. That's when sunlight warms one side, it re-radiates heat, and the tiny push slowly changes the orbit. For something fresh from interstellar space, with unknown spin and surface, you don't assume it away. You test it. Now, here's the part where I need you to hold two ideas in your head at once. Idea one: a small drift does not mean a huge mystery. Idea two: a small drift can still be the start of a huge discovery. And the reason is simple. We've only seen a tiny number of interstellar visitors. The sample size is laughably small. We're basically judging a whole class of objects from a couple of weird strangers who walked into the party. That's why people bring up one I Oumuamua. That's why people bring up two I Borisov. That's why Harvard-Smithsonian Center for Astrophysics and researchers like Avi Loeb can stir controversy by saying we should at least consider artificial possibilities. You don't have to agree with them to understand the real. Interstellar objects may not behave like our local familiar rocks and comets. But the responsible move is not to jump to the wild claim. The responsible move is to build a checklist. So here's our checklist. In human language, not textbook language. First, do the numbers show a consistent drift over multiple nights from multiple observers? Second, do the numbers point to a force direction that matches sunlight-driven outgassing? Third, do the images show a coma or tail behavior that matches that outgassing? Fourth, do the drift patterns change as the object rotates, like a garden sprinkler turning on and off? And fifth, do different teams reproduce the same result when they process the data independently? This is where the Stanford Ronald Bracewell concept is worth mentioning, not as proof, but as a cautionary tale about imagination. Bracewell talked about the idea of probe-like devices in space as a thought experiment decades ago, and that idea sticks in the brain. It makes people see intention everywhere, so we keep it in the back of our head, and we keep our hands on the data. Now, let's talk about the JWST frame in the title. JWST doesn't drop a frame like your friend posting on Instagram. It's a carefully scheduled observatory. It collects data in specific modes. Then the raw data goes through processing pipelines. Then teams analyze. And different processing choices can highlight different features. So when someone says the new frame doesn't add up, there are a few ways that can be true. It can mean the object's brightness changed faster than expected. It can mean the dust geometry looks oddly narrow or oddly symmetrical. It can mean the tail angle doesn't match the simple expectation for where the sun is. It can mean the object appears slightly offset from where a headline predicted it would be. But this is crucial. A weird look is not automatically a weird force. Pictures can be misleading. The orbit is the orbit. So we go back to the orbit, and this is our next climax moment. If you run a simple gravitational model and the object keeps landing a little off target, you add a non-gravitational parameter and see if the fit improves. If the fit improves a lot, that's not aliens. That's physics doing its thing. But if the best fitting non-gravitational force direction points somewhere that doesn't make sense for sunlight heating, then you have a real problem. And problem is good. Problem means you learned something. Let's make this relatable. Imagine you're throwing a paper plane in a room with a fan. If you pretend there's no fan, you'll keep predicting the plane's path wrong. You'll say, it turned. But once you include the fan, the turn becomes predictable. Not spooky, just ignored. Outgassing is the fan. Solar radiation pressure can be a fan too, depending on the object's size, shape, and dust. So what's the headline getting wrong? Most headlines treat drift like a sharp steering move. But drift in astronomy is often a slow, consistent mismatch that gets clearer over time. And the scary part is not it turned. The scary part is we don't yet agree on what force is causing the mismatch. Now, let's add one more layer, because this is where viewers usually lean forward. Interstellar objects come in fast. That means we don't get forever to study them. There's a narrow window where the geometry is good, the object is bright enough, and the observatories can point at it. Then it fades. Then it's gone. So the pressure is real. It's not panic. It's timing. That's why teams try to combine JWST observations with ground-based tracking. That's why you'll hear ESO, Keck, and other big facilities in the same sentence as JWST. That's why researchers at places like Harvard-Smithsonian Center for Astrophysics stay involved. And that's why older how-to habits from missions like Voyager still matter. Because Voyager 1 telemetry data taught engineers how to treat faint signals and weird anomalies with respect instead of drama. Now, let's address the elephant in the room. When the internet says the numbers don't match, a lot of people mean one of these. The object is moving faster than expected. The object is slowing down. The object is shifting sideways. Or the object's tail is pointing the wrong way. So here's what those actually mean in real terms. Moving faster or slower than expected can be an orbit update. Early numbers were uncertain. Shifting sideways can be a small, non-gravitational acceleration. Tail direction can be dust, physics, and viewing angle. A sun-facing feature can be an anti-tail, which is not magic. It can happen when Earth passes through the object's orbital plane and dust sheets line up in a way that makes a tail appear to point toward the sunday. That's a real effect. It's rare looking, but it's known. So the question becomes, are we seeing a known rare effect, or are we seeing a new behavior that forces new models? And that brings us to another climax. The most honest headline is not "it changed course." The most honest headline is "our simple models are failing, and now we have to upgrade them." Because science is basically that. It's you being humble, getting slapped by reality, and improving your math. Now, let's talk about what a drift again could look like if it's outgassing. Outgassing is not always smooth. It can pulse. It can switch on and off as the object rotates. It can come from one active patch that gets sunlight every rotation. So if observers report a repeating pattern in brightness or repeating changes in coma shape, that fits. That's not proof. It's a fit. And this is why you'll hear people talk about timing like every several hours. If a jet switches on and off with rotation, it can create a repeating non-gravitational push that changes the orbit in a way that looks like a weird drift. Now, if you want a real gut check, here it is. If we were watching something artificial, you'd expect behavior that is hard to mimic with sunlight-driven physics. You'd expect changes that are too sharp, too timed, too directional, too energy-heavy compared to what the sun can provide at that distance. You'd expect a pattern that's stable across different observing angles, not something that vanishes when geometry changes. And you'd expect the orbit residuals to show a control-like signature, not a messy comet-like push. We are not there, not even close. And that is good news, because the most exciting thing that's still believable is this. 3I Atlas may be a natural interstellar body with chemistry and structure that doesn't match the comets we grew up with, which means it's a rare lab sample from another star system. And it's teaching us how wrong our normal assumptions can be. Now, one more climax before we land this plane. Here's the part nobody likes to say out loud. Sometimes the numbers not matching is not because the object did something impossible. It's because we're mixing measurements from different sources with different noise at the edge of detectability. And the fit is sensitive. That's where Arecibo legacy data deserves a quick mention, because it represents an era when radar was king for certain tracking problems. Arecibo is gone, but the idea remains. The cleaner the measurement, the less room there is for fantasy. So what should we do right now as viewers without spiraling? We watch for 3 things. 1, do multiple independent teams report the same drift pattern? 2, does adding a non-gravitational model make the orbit fit dramatically better? 3, Do the images show comet-like activity that lines up with the direction of the drift? If all three line up, the mystery becomes, what's it made of and how does it vent? Not who built it. And if they don't line up, then the mystery becomes even sharper. Why does the drift not behave like known outgassing? That's where new physics or new object types start creeping in. Not aliens. New object types. Okay, let's close this the right way. Right now, the headlines are loud, the numbers are quiet, and the universe has a habit of hiding the truth in the quiet part. 3I Atlas drifting again doesn't automatically mean something is steering. It means we're still in the phase where the best observers and the best models are fighting for agreement. And that fight is exactly how real discoveries are made. If you want the next update, the moment the data tightens and we can say what this drift most likely is, tap subscribe and watch the next video on your screen.